So, how many people do we have tonight?
2, 4, 6. We got it's like 7, 8 guys here tonight.
Okay, cool. And do we have any veterans or active duty?
Ja, er zeggen met de Yes, we do.
Sweet. Well, everyone, be sure to give him or her a high five and thank them for their service.
Okay. All right, we have some high fives going around.
Sweet. Okay, so I'll go ahead and get started. My name is Matt Graeber. I work as a malware reverse engineer at FireEye. I'm part of the Flare team. It's kind of funny. It's a name that started out as a joke that just kind of stuck with us. For anyone who's seen Office Space, it stands for the FireEye Labs Advanced Reverse Engineering Team. So pretty much every day I get at least one new malware sample that I have to analyze and pick it apart and pull out. It's at the company we usually call what we need to pull out typically host-based and network-based indicators. So what is the malware's footprint on disk? For example, does it drop any files? What persistence mechanism might the malware use? Does it touch the registry? Does it create any other artifacts like does it spawn up any processes, create any handles, so on and so forth. And then the network-based indicators should be fairly self-explanatory. What does the malware talk to? So I'd say probably 99 times out of 100, the malware wants to talk to something. It's not really that useful a malware if it doesn't have a command and control server to, say, exfiltrate stolen data or receive commands from the command and control server. So that's really important to us. I think I heard the question. Someone asked where I live. I'm based out of Virginia. I work out of Mandiant's headquarter office in Alexandria, Virginia. I say I work for FireEye because we were recently acquired by FireEye. So I have a great time doing my job. I love it. Okay, so where does PowerShell play into all this? Typically, if you approach any malware reverse engineer and you ask them what their favorite tools are, most likely they're not going to say PowerShell is one of their favorite tools for malware analysis. And most of the time that's for good reason. PowerShell actually has a very niche use for malware analysis, specifically for .NET malware analysis. After all, PowerShell is, I like to say PowerShell is basically just a glorified .NET interpreter. It's a great scripting language, has a ton of awesome commandlets built in, but it's also a .NET interpreter. You have the entire .NET framework available to you. So for, say, malware that was written in C# or VB.NET, or even in some cases we see managed C++, we can use PowerShell to automate analysis of that malware. Going back a little bit into more of my background, so I became interested in PowerShell. I forget the exact year. I want to say it was 2010. It was at DEF CON 18 in Vegas, one of the big hacker conferences. Dave Kennedy and Josh Kelly gave a great talk. It's called PowerShell OMFG. And in this talk, they really brought to everyone's attention in the security community the fact that PowerShell could be used for evil. Indeed it can. In my opinion, it really is like the ideal post-exploitation platform. And at the time when I saw that talk at DEF CON, I was a red teamer on the Army Red Team. So I was doing a ton of pen testing and threat emulation at various military bases around the world. And both myself and you may have heard of him before, Chris Campbell. He's ObscureSec on Twitter. We both became like very passionate and interested in PowerShell and use it on almost a daily basis during some of our assessments. So one of the first things that I did with PowerShell was a common task as a pen tester is to run shellcode, which is basically like assembly language instructions that execute a malicious payload. For those of you who may be familiar with Metasploit, one of the common payloads is Meterpreter. It's basically like a full-fledged, fully in-memory backdoor. It's great. So one of the first things that I wanted to build on PowerShell was something that would get Meterpreter up and running. And there's various shellcode payloads that enable you to do that, but none of them were written in PowerShell. And the benefit of PowerShell as a tool that could execute shellcode is that you don't have to drop an executable to disk. At the very minimum, you would only have to drop a PS1 file to disk, or you could do everything via a one-liner and say just download, like using what is it, net.web client, just straight up download the contents of your malicious script and then invoke that all in one line using invoke expression and using PowerShell.exe. So one of the first tools that I wrote was a shellcode runner that would get Meterpreter up and running and enable us to move laterally across the network that we compromise and exfiltrate data and that sort of thing. So from there, as I began writing more and more offensive security tools in PowerShell, I wanted to organize everything properly, and the result of that is PowerSploit. PowerSploit is a series of modules designed pretty much exclusively for offensive security. It's grown a lot over time, and in my opinion, it's kind of outgrown its original scope. So my intent is to make sure that it's purely an offensive PowerShell module. Over time, I added a bunch of reverse engineering scripts to it, and I'm going to be pulling those out this week, and I'm going to be releasing a new reverse engineering PowerShell module. So that's going to be dedicated to reverse engineering malware, obtaining Windows operating system internals, that sort of thing. So keep an eye out for that. So with that, let me go ahead and jump into what I'm going to be presenting. Okay, so I already kind of touched upon why I like to use PowerShell for specifically .NET malware analysis. But specifically, the reason it's really good, besides the fact that PowerShell is, a great interface into the .NET framework, is the fact that in .NET it has something called Reflection API. So what Reflection enables you to do is do some really cool things. So the first being, it allows you to perform type introspection. So let's say I have a malware executable, say like evil.exe. I can load that exe. So while I'm doing all this, I'm doing it in a VM that's not connected to the internet. We want to practice safe malware analysis here. So within my PowerShell session, I can load the exe in memory, and then I can use .NET to ask certain questions of the malware. So type introspection is where you're asking of the malware, hey, what classes have you implemented? What methods have you implemented? What properties in various classes have you implemented? And then from there, using this Reflection API, say there's a particular method that you're interested in, and a really common method that you'll see in like heavily obfuscated .NET malware is a string decryption method. So there may be one or more arguments that don't make any sense to you just when you're reading the code, that when you pass them into this method, it automatically craps out a string that's human readable. So one of the things that I can do using reflection is get a reference to, say, that string decryption method, and then I can dynamically invoke it. And I'll show you how to do all this as I go along. So that's really cool. So what that enables you to do is, instead of spending all this time reverse engineering the malware, you know, like say, I mean, there's various tools to do reverse engineering and like disassembly and decompilation of .NET executables. One of my favorite tools is ILSpy here. It's a free tool. It works 9 times out of 10 for me. Sometimes it does crash depending upon the obfuscator that was used. But what the Reflection API enables me to do is, instead of spending all this time reading this code and trying to figure out what the malware does, say if I recognize that string decryption method, well, I can pull out all the arguments to it and then invoke it dynamically and have the malware do the work for me, instead of spending hours or days or weeks trying to figure out how this string decryption method was implemented. So this saves me a ton of time. Okay, so the scenario for this talk is, now can everyone see my screen okay? Okay, I'll assume that no response means that we're good.
Yep.
Yeah, we're good, Bo?
Yep.
Okay, cool. Okay, so this first file here is the .NET malware that we're going to be looking at. I was just browsing through various malware repositories. I think I got this one from a site called VirusShare. I was just searching for .NET malware for. Lately, I've been researching various obfuscator implementations and ways to efficiently reverse them, and I stumbled upon this one, and I thought it was pretty good. You'll see it's not named .exe. The way most malware repositories name things is that they'll just name the file based on the hash of the file. And that way, so in this case, because it's a bin file, I can't just double click it and, you know, accidentally run my malware. But again, we are running everything within a VM that's not connected to the network, so in that respect, we are relatively safe. Okay? All right, so this is what we're going to look at. Bear with me here. Now, whenever I get any malware sample, whether it's a .NET malware sample or, say, something that was written in C, I'm always going to throw it into a PE, portable executable file editor. And one of my favorite ones is CFF Explorer. There's also a commercial version of it called Cerberus Profiler. It's one of the best PE file parsers out there. The commercial version parses all kinds of files in addition to PE. So it'll do like Linux ELF files, jar files, Flash files, jars. It'll even parse and disassemble fonts. Funny enough, fonts have built-in programs within them, and attackers know this really well because attackers realize that fonts are rendered in the kernel. So if you can generate a malformed font such that it triggers code execution in the kernel, then you go from 0 to hero, and you're automatically running in ring 0 in the kernel, and you know at that point you can do whatever you want. But anyway, so it's a really great tool. Let me zoom in here. So I've opened up our malware sample, and when we're looking for specifically .NET executables, there's going to be a few things that I'm looking for. So let's just kind of go through here sequentially. The first part of any PE file is going to be the DOS header, and many of you are probably aware of what the first 2 bytes of a PE executable are, and that's hex 45A or MZ. I can't hear any of you, but if anyone can yell out what MZ stands for, then you definitely get brownie points for that. So there's 2 fields in the DOS header that really matter to us. The magic field, the 45A, the MZ, to indicate that we're dealing with a PE. And then just the last field, and I'll try to keep my scrolling to a minimum here so that your eyes don't burn. The last field here, ELFA new. This is the pointer to the next field in the PE header, which is the NT headers. So here's the signature here, hex 5045. The ASCII representation of that are the letters PE. And then within that, there's the file header, and there's some interesting things in here. A lot of malware analysts are very interested in the compile time date stamp. So this particular sample apparently was compiled June 19th, 2014. This is easily modified. This can be easily modified, so you can't always trust this that it's actually valid. But still, a lot of malware analysts like to use this as part of their intel on a particular malware family. Also, we show that this is designed to run on x86, so a 32-bit Intel processor. Next, we have the optional header. There's not going to be anything too relevant here related to .NET samples, but if we go into here, the data directories, and scroll down a little bit, the very last entry here, the .NET RVA, so RVA stands for Relative Virtual Address, and .NET directory size. If both of those are populated, then that indicates that you're dealing with a .NET executable. Okay. Another aspect of .NET executables is going to be the fact that that there's only a single import. So when I say imports, executables rely upon third-party functionality. In most cases, that's going to be like third-party like Windows functionality, like say from the Win32 API. So a lot of EXEs, DLLs are going to import functions from, say, kernel 32, NTDLL, those sorts of things. And so within CFF Explorer here, we click on the import directory, and then click on the module or DLL that this executable imports. And in the case of a .NET executable, it's always going to, it will only import mscoreee.dll, and the function that it imports is called _corexe main. So when you double click that .NET executable, there's a bootstrapping process that occurs. That the .NET runtime has to get started from, so it goes from like native code execution at the assembly level, and then when corexe main gets started, that's what starts up your whole .NET runtime and allows you to interact with the .NET framework. Okay. Now, one of the reasons I really like CFF Explorer or Cerberus Profiler is that it's one of the only tools out there that parses the .NET directory of a portable executable. So I use this all the time during the initial phases of my malware analysis of potentially malicious .NET executables. And so I've clicked here on the .NET directory, and really there's only two things that I'm interested in here. So flags, and I can click on the flags here. And what this tells me is that it's implemented in IL only. So IL stands for intermediate language. When you compile .NET code, so whether it's written in C#, F#, VB.NET, whatever, most of the time that code is going to be compiled into an intermediate representation, or it's also referred to as bytecode. So it's not actual like raw assembly instructions. Initially, the .NET interpreter will interpret those instructions, and then it has a process whereby if that code gets interpreted enough times, then it'll use something called the JIT compiler, so the just-in-time compiler, to take those bytecodes and compile them into machine assembly instructions. So the majority of the time, .NET executables are going to have this flag set, IL only. One exception to that would be when native entry point is checked. That usually means that the executable was compiled with something like managed C++. And if that's the case, the PE file format doesn't differ a whole lot. But there's just some extra bootstrapping steps that need to go on before the executable can start interacting with the .NET framework. Okay, so within the .NET directory, that's the first thing I'm interested in. The other thing I'm interested in is the entry point token. Okay, so the entry point token represents the first method that gets called within your .NET executable. So if you're writing an exe, say in C#, this is most likely going to be your main method. So what token means is, so pretty much everything in .NET, whether it's a type, a class, a method, a property, a field, an event, has a unique numerical identifier associated with it. And that's called a metadata token. All methods will always begin with 06. Well, I should say all methods that are implemented within your executable will start with a 06. So that first number, say the 06, so in this case our entry point token is 06, 000004. 06 indicates that it's a method, and the 04 indicates that it's the fourth index into the .NET method table. Okay, so let me show you what that method table looks like. So over here on the left, I'm going to click on tables, and we have a few things here. All right, so I mentioned that 06 refers to methods, so I can expand this here and click on this. Okay, and so this is going to be our entry point method, so think of it as main. But if you are writing something in C# or any .NET language, you actually, it's not required that your entry point method be called main. You have to jump through some hoops to do that, but there's no reason that that you couldn't rename it something else. In this case, in this malware sample, what the author did was when they ran it through an obfuscator, the obfuscator renamed all of the methods that it could rename to basically unprintable Unicode strings. So that's this like little squiggly thing here that you're seeing is some unprintable Unicode string that really makes no sense to us and makes my job more difficult because I can't go off the names of like the original methods and variables and whatnot. So, but that's okay. We can work around that. Another thing worth pointing out is one of the first things that I do when I get a .NET malware sample is I'll click here on the module field, and what this does is so you see gaga.exe. What this is the original executable name associated with this executable when it was compiled. Okay, so the attacker could rename their malware on the file system to whatever they want, but if they're if their Visual Studio project was called Gaga, and then they go to compile it, gaga.exe is going to be baked into the executable. So this can usually yield some interesting intelligence. You know, I mean, the malware authors will usually rename their executable, but they usually don't realize that the original executable name is right here in the PE header. Okay. Now there's a lot more fields within the .NET PE header that are useful to a malware analyst, but in the interest of time, I just can't go through all of them. Okay. All right. So at this point, I have determined that we are dealing with a .NET executable. You'll also hear me refer to them as .NET assemblies. Think of an assembly as like the wrapper for all of the code. And within the assembly is a module. As I showed you here, we have the gaga.exe module. And then within a module, that's what contains all the code. So all of the types, classes, methods, fields, parameters, what have you. Okay, so we know this is .NET, and we know something funky might be going on because when I went to the respective entry point method, so the fourth method in the method table, I would expect to see main right there for an exe, but it was something that was, totally unreadable to me, which raises my suspicion a little bit. So the next thing that I would do is throw the executable or DLL into my decompiler of choice. In this case, that's ILSpy. That's my go-to decompiler. There's a lot more out there, so some of you may be familiar with .NET Reflector is one of the big ones. That's one of the few commercial decompilers out there. I have mixed feelings about that one. I think you can get a lot more functionality from some of the free ones than you can .NET Reflector, but it has its purpose. The only thing is that it doesn't really deal with obfuscated code that well. For unobfuscated code, it's great, and it has a great Visual Studio plugin. But ILSpy is one of my favorites. Again, sometimes it does crash. In that case, I can try reverse engineering my malware in other tools. So there's also Telerik, just decompile. There's also JetBrains.peek. So I'll use both of them as a backup. But we're interested in our malware here, so I've got an ILSpy. And here, let me show you a normal .NET executable. So I put ILSpy into ILSpy, and one of the things you can do here in like the main window when it loads is it shows you the entry point method. In this case, for ILSpy, it's the main method, and I can just click main, and it'll take me right to it. It's kind of nice. Here I can click the back button, go back to where I was, and like you can see all of these things. These are all assembly attributes applied to the executable. Okay, so that's what normal. That's what a normal executable looks like. Let's look at an obfuscated executable, the malware in our case. Okay, so a couple things stand out to me. The first being the entry point. It's got these weird characters in here that don't really make much sense to me. When you see this sort of thing, that usually means that that everything was that all of the method names, the namespaces and types were obfuscated and renamed to something unprintable. And ILSpy doesn't really know how to handle those too well. And what I mentioned before was that you can click on the entry point method, but in this case, in like the super obfuscated stuff, like I can't click it. So we need a way around that. Like we need to have an alternate method of drilling down and trying to decompile our main method. There's some other attributes that stand out to me. So like smart assembly right here, you can just Google that, and it's one of the popular commercial .NET obfuscators out there. It's pretty good. Another thing worth noting is the suppress ILDASM attribute is applied to this. ILDASM is a free .NET disassembler that you can get from Microsoft, and when ILDASM recognizes this assembly attribute, it will honor it and say that it's unable to disassemble it. Fortunately, all the other disassemblers and decompilers just ignore this attribute, so you can usually safely ignore that. But this is common to see when you're dealing with obfuscated .NET executables. Okay, so all right, now I can start talking about PowerShell. So the first thing that I want to do is I want to know the metadata token of the entry point method, and we determined that earlier just by looking at the at CFF Explorer. If you recall, it was 06000004. I want to use PowerShell to get to that same conclusion. And the reason I'm interested in the metadata token is because everything was renamed to like these unprintable like Unicode strings, I can't really reference methods or types of classes by name. So like I can't use reflection in PowerShell and type in like say give me a reference to the main method because it's some like garbage that I don't know how to type. Fortunately, you can reference these methods using their metadata token. Okay, so let's look at my script here. So the first thing I'm going to do is I'm going to read in the path to the malware. I'm going to read it in as a byte array, and then using system.reflection.assembly, the static load method, I can load that byte array in memory and load the malware into my PowerShell session. Now, at that point, once I do that, it's not going to execute the malware. So we're still kind of safe at this point, but you should still be doing it in a VM anyway, because once you start dynamically invoking some of those methods within the malware, then there's a chance that you can invoke some of the malware's functionality. And if you haven't fully reversed it yet, then you really have no idea what that malware is going to do to your system. So, you know, safe practice, again, always do this in a VM. Okay? Next, I'm going to get a reference to the first module within our malicious assembly. So recall I said an assembly was kind of like the wrapper for everything, and then there can be one or more modules within an assembly. 9 times out of 10, there's only going to be a single module. So I'm just getting the first module, even though there's only one module. And then once I have that module object, I can start doing some cool things. So let's do module get member, and there's some interesting methods here. So we have resolve field, member, method, signature, string, type. I'm interested in the resolve method and what that accepts is, so this takes an integer value, which is the metadata token of the method that you're interested in. Now let's figure out what metadata token I'm interested in. Specifically, I'm interested in the metadata token for the entry point method of the executable. In other words, the first thing that's going to be executed when you double-click the malware. Okay, so here within the assembly object, I can reference the entry point parameter, and what this gives me is some information about the entry point method. So here it's telling me that it's a method. The containing module for it is gaga.exe, which we saw in the PE parser previously, and we have a metadata token associated with it. So we saw in the PE parser previously that was 06000004. And that was in hexadecimal. Let's see if this one matches up. So what I can do here is I can do, to convert it to hexadecimal, I just call the toString method, and then I give it a hexadecimal format specifier of width 8. And indeed, that is the entry point metadata token that we're interested in. Now, going back to ILSpy, one of the cool features in one of the latest versions of ILSpy is that you can go into View, Options, Display, and then you can click on Show Metadata Tokens. So then when you expand this here on the left, it's going to show you the metadata token of each respective item within that executable. So the ones that start with 0, 2 are all types or classes basically, and then within each class there's going to be various fields, parameters, and methods. So here is the method that we're interested in, 06000004, and if any of you here are familiar with C#, this is what we're looking at. This is a decompiled representation of the executable in C# syntax. And because this is obfuscated, it looks like total garbage. It's really hard to just sequentially read this and follow what's going on here. So like in this case, what we're seeing here is an example of control flow obfuscation. What a lot of obfuscators do is it'll take the logic of a program, break it up into chunks, and then rearrange all those chunks and then put them into a switch statement, and then just iterate through like each case statement in the switch statement until you execute all the original code. That makes it really hard to just scroll down and see what's going on. But I spent a little bit of time looking at this, and what stood out to me was this here. We have a method that returns a string. It's a static method that takes 2 integer arguments, and again it returns a string. Having looked at enough.NET malware, that's something that stands out to me, because a lot of obfuscators will take human printable strings, obfuscate them so that none of those human printable strings are resident in the executable, and then they'll do something like this. They'll encrypt the strings and then take a very specific set of arguments to decrypt them. So I would click on this. It takes a minute to decompile, but again, it's just another pile of garbage. Something that I don't really care about the implementation. If I can just dynamically invoke it in PowerShell and have it give me the answers that I'm looking for, then that's an easy win. So I'll show you how I did that here. And that there was one instance in particular that I was interested in. It was when the text variable was being assigned. Okay, so this one right here. So I just went through and I looked at a lot of these instances. I pulled out the arguments, and this is what I did in PowerShell. Okay, so if I was to click on this method, it would show me the metadata token for it here on the left. And in this case, the metadata token of this candidate string decryption method is 0645 in hexadecimal. Okay, and I'm going to pass that to the resolve method, invoke that, and now I can start dynamically invoking this method that was implemented in the malware. So here's one example here. This was the first instance of it being called. I'll just go ahead and invoke that. Cool. And it returned to me this unintelligible string. This makes no sense to me. So at that point, I wanted to move on and try some more. So let me just try 3 more that I found while I was looking at it in IOSpy. Okay, we have more garbage, more unintelligible garbage. Let me clear my screen. Try out another one. This one was interesting. And sorry for the fast scrolling. Let me scroll to the top, and hopefully this may stand out to you as something recognizable. Look at those first 2 bytes. 45A, MZ. So this looks like an embedded executable within this malware. So that's cool. So what I could do using PowerShell is I could save this to a variable. So this was the particular invocation that output this hexadecimal string representation of an embedded PE file. Let me save that to a variable. Okay. Now, it's probably pretty likely that the malware is going to take this raw string and convert it to a byte array, and then my guess is load it in memory and then invoke the entry point method of this embedded executable. And indeed, that is the case. So going back in here, so this was the invocation of the decryption method that output the hexadecimal representation of that PE. Let's look and try to find for where this text variable is referenced again. Okay, not text 6. Oh, here we go. Okay, cool. All right, so here's where that text variable is used. It's passed to some method. Again, I don't know what the implementation is, but I can guess. That text is passed to this method, which returns a byte array. So my hunch is all this method does is it takes that string representation, converts it into a byte array that we can work with. So now let me search for where array, the array variable is used. Okay. All right, this is looking good to me as a malware analyst. So here's where the array variable is used. Again, it's passed to some method. I have no idea what it does, but it returns an assembly object, which indicates to me that so the string that was returned from the string decryption method, which was then passed to another method which returned a byte array, was then passed to another method which returned an assembly object. And to refresh your memories, I basically did the same thing. I read in the malware executable on disk, read it in as a byte array, and then I loaded it using the static load method in reflection.assembly. This is basically the same thing that the malware is doing to get this embedded executable loaded into memory. Okay, now now that this executable is loaded into memory, we haven't done anything with it yet. It's loaded, but it hasn't been invoked. So let's see if anything does anything to the assembly variable. Okay. Okay, so here's where the assembly variable is used. This part is going to be a little more confusing because it's not completely evident what is being returned. But so there's 2 method calls being made. There's this first call on the inside here, and if we hover over here, we see that this first method call returns a method info object. So a method info object is identical to, recall I got a reference to the entry point method. So here if I do entry point method dot get type, we have a method info object. Malware is doing the same thing. It's taking the loaded assembly in memory, passing some arguments to it. Again, because the obfuscator is trying to like abstract away any like intelligible meaning from this, so it's just passing in what seems like 2 random arguments into this method, and what gets returned is a method info object. And then after that, we have the next thing that's called, so that this doesn't return anything, but for from what I've seen reversing enough .NET malware, whenever you have something that returns a method info object, it's that method info object, they're gonna call the invoke method on that method info object. So I'll show you what that looks like. So I'm gonna do the same thing that the malware just did. Okay, so we have our encoded PE. I'm going to work with that in a little bit. And in ILSpy, I got the metadata token for the method that returned the assembly object. And then I'm just going to pass it the same arguments that the malware passed it so that I can get a reference to the loaded assembly in memory. Okay, so decrypted assembly is what I called it. Let me show all of the properties here. Okay, so this is interesting. It shows that the entry point method of this is actually called main. So this is looking pretty good for me so far as a malware analyst, because I interpret that as this embedded executable that gets loaded is probably not obfuscated. If they didn't bother renaming the main method, then there's a good chance that I'm going to be able to analyze this. Oh, and here's the original name of the executable, j.exe. So even though this embedded executable has not touched disk, I can still get all kinds of insight into it, like when it was compiled. Okay, so the next thing that the malware did, recall, was it took that assembly object, passed in 715640 as its arguments, and it returned a method info object. All right, so, sorry, let me go back real quick. I'm going to do the same thing in PowerShell. I'm going to invoke this method in PowerShell dynamically using reflection. So I'm going to resolve the method using the metadata token, which I got from ILSpy, and then I'm going to pass in the same arguments that the malware did to get this method info object. So let me execute that, and then let's check out this target method. Okay, scroll up, and it's main. Okay, so what the malware resolved was the main method of the embedded .NET executable, and then my guess is this outer method that's called is going to just invoke the main method dynamically using reflection, the same techniques that I'm using as a malware analyst. But at this point, my job using PowerShell is pretty much done. The only thing left for me to do is, well, I still have more malware to analyze. I have this whole embedded .NET executable that I need to analyze. So let me dump that to disk. Recall, let's see, our encoded PE was this hexadecimal string. So I'm just going to use native PowerShell instead of, so what I could do is I could dynamically invoke the method within the malware that converts this string to a byte array. But I mean, I'm comfortable enough with PowerShell, I can just do it in native PowerShell. So what I'll do here is I'll take the string, I will split it using a regex, and so here I'm saying split on every two, or basically split on every hexadecimal byte. And what that looks like is this. Sorry if the scrolling is making your eyes bleed. So it will split into each respective hexadecimal byte, but it will insert a new line in between each one. So I'll just pipe it to where object, where it returns something. So it will only output the hexadecimal strings and not those and not the blank lines. And then what I'll do is I'll cast the string as a byte, and the way you do that is you have to prefix it with 0x first. So take like 30 hex 32. Okay, so that's the string hex 32. But then because it's prefixed with 0x, I can explicitly convert it into a byte, whose integer representation is 50 in this case. Okay, so I'll do that in PowerShell. This isn't the most efficient thing to do, but it takes a few seconds to complete. Okay, and now I have my fully decoded PE. I can write it to disk now, so I'll go ahead and do that. Well, I've already written it to disk, so I don't need to do it again. And I just named it decoded.exe. And then we start this iterative process all over again as a malware analyst. Fortunately, as I suspected earlier, this was not obfuscated. So here I can click on the main method. I can click on this. So I mean, yes, like the namespaces, the class names, and the method names were renamed to stuff that doesn't really make sense to me, but at least it's readable. And here, like this decompiled output now looks really good to me. Like this is just like I'm reading source code. So now I can easily use ILSpy to pull out those network and host-based indicators. I'm not going to go over that since it's not at this point. Like we're pretty much done with PowerShell, unless there's any like additional obfuscation going on, or say if there's some like embedded encrypted data, or some like encoded strings. Like I could certainly use PowerShell to automate any additional analysis if I needed to. Again, this malware was written in .NET. PowerShell is a glorified .NET interpreter. If there's any additional analysis that I need to do on this sample, PowerShell is going to be a great tool. Okay, and yeah, just for your reference, this is just basically a generic backdoor. It's pretty fully featured. I think there's like a reverse shell component. It will do screen captures, screenshots. I think you can upload and download files. It's pretty much your typical run-of-the-mill backdoor. So, I mean, well, it's still scary. Like, you don't want this on your computer. But to me, as a malware analyst, like, this doesn't really stand out to me. This is just kind of run-of-the-mill crap that I see more or less every day. All right. So, with that, I will open the floor to questions and try to clarify some of the points here. I apologize. I probably rushed through some things, and it may have been hard to keep track, but just feel free to hit me with your questions.
All right, thanks, Matt. Any questions for Matt?
So what's your workflow as far as doing malware, and do you use PowerShell at the time only on .NET objects, or try to use it with other things that are malware at all? You know, it's like this would probably L files, but.
Sorry, the question wasn't very clear to me, Bo. Would you mind repeating it to me?
What's like a workflow for analyzing malware? Thanks.
The question is, what is your workflow for analyzing malware?
Okay. Well, so for .NET malware, what I just showed you is more or less my typical workflow. If it's any other style of malware, and in most cases, I'd say like .NET malware probably comprises about, I'd say 5 or 6% of the malware that we see. Everything else, I mean, the vast majority of it is either like compiled C or C++. In which case, as with all malware, one of the first things I'm going to do is look at it in a PE editor. And then after that, I'll probably throw it into one of my favorite disassemblers and analysis tools, IDA Pro. That's like the staple reverse engineering tool that pretty much any reverse engineer should have and be familiar with.
Hey, we're having kind of some audio issues with that. It's kind of going in and
some
out.
audio issues.
Can you hear me pretty good on my end?
Yeah, I can hear you.
Yeah,
do you
you're coming in kind of spotty now.
Okay. Do you want me to stop presenting?
Yeah, if you don't, yeah, that might help out. Yeah.
Okay. How do I sound now?
Alright.
Do I sound any better?